Um, yeah, so this problem is called purchasing milk, right? Um, yeah, so yeah, you want to you have like each option is like some power of 2 buckets of milk, and you have to pay like AI moonies. Um, and then you're given an integer x, and you want to find the minimum cost to purchase at least x buckets, right? Yeah. So like some observations you can make, right? So let's say that in the input, like yeah, I'll just write some sample input. Uh yeah, so maybe this is like yeah, 4, 5, 6, 7. Uh yeah, like 50, right? Yeah. So this is like the price for 2 to the 0, and 2 to the 1, 2 squared, 2 cubed, and then 2 to the fourth. One observation is that like you never actually need this 50 because it's like much smaller than 7, right? So like instead of getting like this is a 2 to the fourth place, right? Instead of getting a 2 to the fourth bucket for cost 50, it's always better to just get two cubed buckets, and the cost will just be 14. It's like 2 times 7, right? So you can take out this 50 and just replace it with 14, right? Yeah, I'll just like visually, I'll try to visualize it. So yeah, so if this one is like very cheap, let's say I'll just denote the height as the price. Um, and then, so this is like AI, and this is AI plus 1, right? Um, Basically, it's better to get 2 of these than to get this, right? So I'll just remove this, and then basically you can replace it with this, right? Yeah, so yeah, there's basically this observation. So then you kind of have a condition like AI is should be less than or equal to 2 times AI minus 1, right? Yeah, so yeah, uh, we can kind of go from left to right to pre-process the input to make sure that this condition holds, right? Um, yeah, let me see if any of the sample cases, yeah, let me see if any of the sample cases have a nice way of writing this. Yeah, okay, so let's look at the sample case. Um, yeah, so this says the four costs are 10, 25, 30, and 70. Just erase this. So I'll just write that here, 10. Use black. Okay, 10, 25, 30, and then 70, right? So let's just replace this with 20, right? You can just get 2 buckets of this for a cheaper price. This stays as 30, right? This is better than getting 2 of these. And then let's replace this with 60, right? Okay. Yeah, so we can kind of pre-process this as like this. If you wanted to like visualize it as a for loop, you just do like for I equals 2 up to n. AI is min AI, and then 2 AI minus 1, right? So let's just assume this stuff is pre-processed. So it always holds for every I. AI is less than 2, or less than or equal to 2 times AI minus 1. Just like assume this about the input, right? Right. So basically what this is telling us is that AI is the minimum cost, uh, min cost to get 2 to the I minus 1 buckets, right? Okay. Yeah, so let's just assume this, okay. Yeah, let's just assume this holds for all I, right? AI is up to 2 times AI minus 1, right? Let's go back to the problem, right? Uh, you want to find the minimum cost to purchase at least X buckets of milk, right? So the key thing here is like at least X buckets, right? Yeah, so if it asks for like exactly X buckets, it turns out that's actually something we can do pretty easily, right? So let's write x in binary. So let's just consider the simpler version of the problem where it's asking for the minimum cost to purchase exactly x buckets, right? So that x will be in binary like this, right? And basically, we just need to find the cheapest way to get each power of 2, right? So it's going to be the cost of this plus the cost of this plus the cost of this. So if we're only looking for exactly x buckets, then the answer would just be a of 2. Like a of 1 is the minimum price to get 1 bucket. A of 2 is the minimum price to get 2. So it'll be a of 2 plus a of 4 plus a of 6, right? So in the case where it's exactly x, we've already solved the problem, right? But let's consider we're purchasing, yeah, I'll just write this on the left. So we're purchasing y buckets where y is greater than x, right? So if you look at, so when you see something is, uh, uh, sorry, I don't know Hindi, but um, yeah, okay, yeah, okay, uh, yeah. So when, yeah, so yeah, so like this problem is kind of asking about bitwise things with powers of two, and when you want to when you consider like a number is greater than another, uh, like in terms of the bits, what it actually looks like is, let me just draw y over here and then draw x over here. So for some prefix, they'll be equal, right? So for example, this might be 0, 1, 1, 0, 1, and then this might also be 0, 1, 1, 0, 1. And then at some bit, y has to equal 1, and then x has to equal 0. And then this suffix can be anything, and then the suffix can be anything, right? Right. This is something you should always consider when like you're dealing with bitwise things or powers of two, and you're considering like one number is greater than the other, right? So up to some prefix, they're equal. And then after that point, the bigger one is equal to 1, and then the smaller one is equal to 0. And then after that, both of them can be like anything you want, right? One observation we can make is that if y is greater than x, and let's say that they disagree at index, like yeah, at index I, let's say they disagree at index I. If you want to spend as little money as possible, subject to this, so here I wrote it can be anything, but it's always cheaper to just make these all zeros, right? Since you want to spend as little as possible, right? Um, it never helps to like set one of these to 1. You just have to pay more, right? So in the case, so when if y is greater than x, that means that for some bit, the ith bit of x is 0, and then the ith bit of y is equal to 1, um, right? And then you just find the cost of this, right? Um, yeah, so yeah, so for the case where y is equal to x, you just add the cost of those powers of 2. And the case where y is greater than x, you can do casework on where these bits disagree. And before that, they're all equal. And after that, they're all equal to 0, right? And then, yeah, what you can do is just, um, the answer for this case I is going to be the sum of the costs corresponding to these powers of 2, right? Yeah, any questions? I'll just summarize what we did again. Yeah, I can also like rewrite this in a for loop, right? Yeah, so basically we're considering two cases, either y is equal to x, in which case you just add these powers of 2, or y is greater than x, right? And if y is greater than x, basically what that means, there's a bit where there's equal to 1, that is equal to 0. Everything before that are equal. And it never helps us to set any of the later bits to 1, right? So we just make them all zeros, right? Yeah, so yeah. Yeah, so if I were to write this like as a for loop, so for I equals 0 to um uh wait. Yeah, okay, yeah. yeah, also important thing is that x is like 10 to the 9, right? 0 up to, so you only have to care about like 30 values, right? 30, and then if x bit is 0 and y bit is 0, 1, sorry, x bit is, sorry, ith bit of x, I'll just write it as xi equals 0 and yi equals 1, then basically calculate the cost of the string. Yeah. And then one detail you need to be careful about is that n is up to 10 to the 5. So you also have to consider like x is like starts with a 1, or like sorry, y starts with a 1, and then it's like 10 to the 5 zeros. But you can just do that like outside of this for loop. So you can have this for loop for I up to 30. And then if I is greater than 30, then you just take the max, you just take the min of the answer you get from here, and then the values of your input that are greater than 30, right? Yeah. So that's how you do this problem. Any questions? Yeah, so I'll just summarize. Yeah, so observation is like, yeah, we can like assume things about the input, right? Because if this one is small and then this one is like huge, then we can just like replace this with 2 times the small number. So you can just do a forward pass to like make the input a bit nice so that like the ith value gives the true minimum cost of having like exactly 2 to the I buckets. Yeah, and then we just do casework. There's like only 30 relevant cases for how many buckets we should actually buy, because y is greater than or equal to x. It's either equal to x, in which case you use these 1 bits to calculate what you need, or it's greater than x, which means it's equal to 1 at some bit where x is equal to 0 and the rest are equal to 0. So you just add these 1 bits. Yeah, and then there's the third case you have to be careful about where, yeah, maybe like an is super tiny and n is like 10 to the 5. Um, yeah, but that's how you do this problem. Yeah. Um, yeah. Uh, yeah, I guess maybe for, I haven't thought about this too much, but maybe for n equals 10, like you can use some fact that, like, uh, or like the number of buckets is only going to be up to 1000. But yeah, I haven't really thought about those details too much. Yeah, but that's how you do this contest. Yeah, so yeah, I guess the results should probably come. Generally, they come up in the next few days, maybe in the weekend or something. Yeah, I think this is a good problem to upsolve. Yeah, just to I think bitwise problems come up a lot in maybe not just USACO, but just in like competitive programming in general. Yeah, and I think this is also like a pretty educational problem. At least the brute force part, like how to like iterate over subsets and like the bit manipulation parts. Yeah, that's also something that comes up pretty often. Yeah, this problem's a little ad hoc, but yeah. Um, yeah, I think like, yeah, if you get like very experienced, like you can probably solve this in a few minutes. Maybe some of you actually did, but yeah. Yeah, that's all I have for this contest. Yeah, right. Yeah, I'll just take any questions for the next few minutes. Thanks.
Arvind, could you stay on the slides cover the Brown's problems topic? Because some
Oh,
YouTube,
yeah, sure,
yeah,
of course.
some YouTube they didn't see it. Yeah, thanks.
Okay, yeah. Yeah, yeah, yeah. Yeah. Um, yeah, so I would classify the first problem under ad hoc. Like the biggest part is like making the observation that you go backwards. Yeah. For those of you who haven't like heard of the concept of ad hoc, um, I generally say like ad hoc problems, they don't really fall into any specific topic. They're more about making observations. I think the meaning of the word ad hoc is like the problem is original and there's like not that many problems that are like it, or it's like different every time. Yeah. And then the Muhunt problem was, yeah, this is a brute force problem. Also a good exercise in bit manipulation. Yeah, there's also a good exercise in like constant factor optimization. And a lot of problems, they don't really like require much constant factor optimization, but yeah, it can be good to be good at that kind of stuff. Yeah, and then purchasing milk is more like about bitwise problems and like making, yeah, I guess there was a greedy observation we made in the beginning where like the buckets sizes have to follow like some certain structure, so you can't have like one small followed by one huge one. Yeah, cool.